Hi everybody, in this video I'm going to go over APEX section 7.2.3, which goes over melting and boiling points. This is the part 1 video, and then we're going to have a part 2 video that we'll watch tomorrow. So before we really get into this, I want to make sure we know what melting and boiling point is. So the melting points, I want to point out that the melting point is the same as the freezing point. And that's just the temperature where your substance goes from a solid to a liquid. So for water, that happens at 0 degrees Celsius. Okay, so 0 degrees Celsius is the melting point, and it's also the freezing point. It's the point where it's going from a solid to a liquid or a liquid back to a solid. Okay, boiling point is the point where you're going from a liquid to a gas. And that happens at 100 degrees Celsius for water. Okay, so we need to have an understanding of what melting and freezing points are and boiling points are to do anything in this section. Okay, so moving on. Substances that have stronger intermolecular forces are going to have higher melting points and boiling points. We already talked about this last week. And we said that if you have a stronger intermolecular force, that means that the particles are being held together more strongly, so it requires more energy and a higher temperature for it to melt or for it to boil, okay? And we remember that hydrogen bonds are the strongest intermolecular force, then dipole-dipole, and then van der Waals, okay? So we're going to go over an example here of how we can apply this. So we have 4 different molecules here, and we need to match the molecule to its boiling point. And here are our options: 46 degrees Celsius, negative 196 degrees Celsius, 100 degrees Celsius, and 61.7 degrees Celsius. So what we're going to do is we're going to go through each molecule, we're going to sketch it, figure out its intermolecular force, and then use that to find the boiling point. Okay. So N2, we have 2 nitrogens bonded together. And since they are the same atom, they're going to have no electronegativity difference, so they're going to be nonpolar. Okay, so we remember for nonpolar, there's no permanent dipole, so they can only interact if by chance all the electrons end up being on one side for one atom and the other side for another molecule, I should say. Okay, so then these can interact, but only for a quick second, and we remember these are called van der Waals forces. Another name for that is London dispersion. That's the same thing. And they're also sometimes called induced dipole. So if you see any of these names, you know it's the same. And this, we remember, is our weakest. Okay, so now let's look at water, and we've drawn water 1,000 times. Okay, and we remember that water is polar, so it has a partial negative on the top by that oxygen, partial positive by that hydrogen, and so our positive and our negative are going to interact. Now we also remember that when we have hydrogen that's bonded to nitrogen, oxygen, or fluorine in a polar molecule, you get hydrogen bonding. So the strongest intermolecular force for water is hydrogen bonding. It also has dipole-dipole and van der Waals, but we're just going to write here the strongest. Here, let me add that up here. Okay, so these interact pretty strongly. All right, now let's draw CHCl3. Oh no, you know what? This is a typo. This should be CH3Cl. Okay, I apologize for that. So, okay. So you see we have a different electronegativities, And chlorine is a lot more electronegative than carbon or hydrogen, so it's going to be partially negative, and this end is going to be partially positive by the hydrogens. Same thing over here. Okay, so the partially positive end from the hydrogen end is going to be attracted to the partially negative end, and we know these are polar molecules, but you don't have hydrogen bonded to nitrogen, oxygen, or fluorine. So it can't be hydrogen bonding, but it's stronger than van der Waals, so we have dipole-dipole. Okay? All right, let's do our last one. Carbon disulfide. So we have carbon with sulfurs on either side. Okay? And we can see there is a separation of charge, but it's symmetric, so this is non-polar. So again, it can only interact if by chance all the electrons end up on one side of the molecule, and they can interact, and that would be, again, van der Waals. All right, so now we know what is the strongest intermolecular force for each of these, and we know that stronger intermolecular forces have higher melting and boiling points, so now we can start matching it up. Water is the only one with hydrogen bonding, which is the strongest, so it has to be the highest temperature, which is that 100 degrees Celsius, and that matches what we just said. The boiling point of water is 100 degrees Celsius. Okay. The second strongest is that dipole-dipole. Okay, so that has to have the second highest boiling point, which is this 61.7 degrees Celsius. Okay, so CH3Cl has a boiling point of 61.7 degrees Celsius. Okay. All right, now these two both have van der Waals. They're both weak. So which is going to be which? Well, we can think about how nitrogen is going to be even weaker, right? Because they're all the same atom, so there's no difference in charge at all. Whereas CS2, there is a difference in electronegativity. It's just that they're symmetric. Okay. And also, we know that nitrogen is a gas at room temperature because most of the atmosphere is made of nitrogen gas. So this has to have a really, really low boiling point. So I'm going to put this negative 196 degrees Celsius, the lowest boiling point for nitrogen. And that leaves this 46.0 degrees Celsius for CS2. Okay, so what we did here is we drew it to figure out if it was polar or not, and then we found the intermolecular force, and then the strongest intermolecular force has to have the highest boiling point, the weakest intermolecular force has to have the lowest boiling point, okay? All right, so a couple definitions here. Volatile. A substance that evaporates readily at a normal temperature and pressure is considered to be volatile. So volatile liquids form a vapor readily, easily, and that's why you can smell them. So perfumes are made up of volatile liquids. That means they form a vapor, they evaporate very easily, and that's why you can smell it. Okay, another term we need to know is vapor pressure. So this is the pressure of dissolved vapor bubbles in the surrounding liquid. Let's just draw a picture to help us understand that. So if you have a pot of water and you see little bubbles are forming, okay, the pressure inside that bubble, the air pressure inside that bubble is the vapor pressure. Okay, so if your vapor pressure in your little bubble is the same as the atmospheric pressure outside of your pot, then your liquid boils. So atmospheric pressure is 1 atm, usually. And if the pressure in your bubble is 1 atm, that means it's boiling. Okay? So a volatile liquid, that's again a liquid that's going to evaporate very easily, it's going to have a high vapor pressure. That means it's going to have a low boiling point. All right? So I want to point out here that evaporation and boiling is not exactly the same thing. Right? So you might see if you have a pot of water that you have steam coming off before those big bubbles start happening, and that would be evaporation. But boiling only happens when the atmospheric pressure is the same as the vapor pressure. Okay, so it's slightly different. All right, let's move on. So the last thing we're going to talk about here is separating mixtures. So if you have a solution, we've been talking about solution, there are ways to separate it out. One way is evaporation, and you already know this way. So if you had a solution of salt water and you let it sit out in the sun, you're going to get just the salt. The water is going to evaporate off, and you have a separated solution. Right? This is how they make sea salt. They take a lot of seawater, they put it out in the sun, the water evaporates, and they're left with just the salt. Okay? A second way to separate mixtures is through an ion exchange resin. You're going to read about this in a couple days in an assignment, and basically what it does is it's a way that they use to purify water, and it swaps out the solute ions so they're less dangerous. But again, you're going to read more about this, so don't worry about that just yet. Okay, the next thing is distillation. This is used to purify liquids, and it relies on different boiling points of substances. So if we have a solution here, and it's a mixture of a couple different things, right? So let's say we have some blue substance and some purple substance, right? You have a mixture of two things, okay? What a distillation does, let's try and draw this. Okay, what happens in distillation is you have your substance and you heat it up under a flame, okay? And then your two substances are going to boil at a different temperature. So if your purple substance boils first, then it's going to evaporate, it's going to go through the tube, and it's going to end up here in your other beaker, okay? And if that continues to happen, then eventually this side will have the pure blue substance, and this side will have your pure purple substance, okay? So it relies on the different boiling points, right? The one that boils at a lower temperature is going to boil out first and separate into a separate beaker, and then you're going to be left with the higher boiling point thing. So for example, if you have a solution of, let's say, rubbing alcohol and water, rubbing alcohol evaporates at a lower temperature, so you're going to have all your rubbing alcohol in one side, and the water is going to be left on the other side, okay? And this is distillation, okay? And the last way to separate we're going to talk about is chromatography. Okay, so chromatography is used to separate a solution for analysis, and it relies on the speed that a substance moves and the interaction between the substance and what's called the mobile phase. Okay, so let me give you an example. A lot of times we use paper chromatography, which is where you get a little slip of paper. Okay, and then you put your substance here on the bottom, okay, and then we put our paper in a beaker that's filled with some kind of mobile phase. Usually it's water. And what happens is that water goes up the paper, and the parts of your mixture that are most attracted to the water come up the most, and then parts that are less attracted come up less far, okay? So in this case, this red component is interacting the most with the mobile phase. And this green part down here interacts the least. With the mobile phase. Okay, so distillation and chromatography, you're not going to have to actually do these things, but we want to know how they are used. So For example, distillation is really good for purifying liquids that you want to use for another purpose. Like if you have a mixture, but you want to use the parts of the mixture, because it separates them and then you have them ready to use. But chromatography is more of an analysis technique. It just tells you how many parts there are, but you can't actually use those parts for anything. Okay? So if you're trying to purify liquids, you're trying to go for distillation. And if you just want to know what things are in your mixture, then you're going to go for chromatography. Okay? So from today, what we need to understand is we need to know what a boiling point and a melting point are, how to relate intermolecular forces to boiling points and melting points. We need to know what volatile and vapor pressure means, and we need to know these 4 different separation techniques: evaporation, ion exchange resins, distillation, and chromatography. All right, thank you very much, and come back for part 2 tomorrow.